Now we'll study single stage cluster sampling further. For simplicity, assume that the cluster size mi's are all equal. So, an unbiased estimator of the population mean is then simply total divided by the total number of element, which is n, right? So n hat, but this is fixed. So if ni's are all equal, then n is fixed. So I mean known, and so the total estimator is ni divided by small ni summation si, and then total I ti, right? So that after that you can see that capital N cancels, and so this small ni and capital N comes here, and then this one is ti. So that's how we get this formula, and then you can define this y bar I u is the ti divided by m, right? So this is in this case m, because mi's are not different, so are all equal. So ti divided by m. So basically this is what? Sample mean over y bar I use, right? Okay, so that is because it's simple enough sampling. So we from each cluster we have a single observation. So observe this y bar IU in sample cluster I. So we get this sample mean as an estimator. For variance, so basically since this is sample this is a sample mean of y bar IU, so we just have a variance, right? So this is a variance, population variance of y bar IU. So this is basically the formula for simple random sampling. Now, to understand the variance formula here, let's consider the following ANOVA decomposition. So we have a Yij observation. So cluster I, element J. So we can have a analysis of variance using between cluster and within cluster. So this is the definition. So basically, the idea is this is a total variance, right? And then here we subtract the y bar IU, and then add y bar IU here. So if you do that, and then we can basically Ij Yij minus y bar IU plus y bar IU minus y bar u. Okay, and then we can write it. We can expand this summation, and plus y bar IU minus y bar u square, and then the cross product term is 0. So the first term is this within sum of square, and second term is between sum of square. So we basically SSB plus SS within equal to SST. So we have this equality, and also we have this equality here. So degree of freedom degree of freedom means that the how many terms are there, and then you subtract by the constraint. So here in SSB you have a n term, ni term, but because you have a subtract here, you subtract 1. So you ni minus 1. And here you have a ni times n terms in the summation, but you have subtracted the mean for each I. So basically you have you need to subtract 1 for each I. So that's why you have this degree of freedom. Here you have a ni times m, but you have a 1 term, so it doesn't depend on I. So you just subtract 1 constant. So this is the degree of freedom. And then mean sum of square is a total sum of square divided by degree of freedom. So this one is SSB divided by ni minus 1, and SS within is also SW square is SS within divided by its degree of freedom. Okay. Now, of course, this S square is this one divided by this one. So this S square is a total SST divided by y and I m minus 1. So this one, the numerator part is SST. So you can write this SST as a sum of these two terms, but these two terms, each one is this one. Excuse me. SSW is SB square times n minus 1. Right? So this one is S within square times its degree of freedom. So that's what we have here. So basically, this is the first term is SSB, second term is SS within. Okay. And so once you do that, then you realize that here ni is large. For sufficiently large ni, so you take the limit, then compare the first term. So that this one doesn't really make a difference. So ni is large, then this one also doesn't make difference. So you just multiply, divide ni, capital Ni divided by ni times m. So that's why you have m here, 1 over m here. And second term is that you have a n numerator, so ni times m minus 1 divided by ni times m. So ni cancels to each other, and the only thing left is this m term. So that's why you get this one. Okay. The variance. So the variance here, the variance of the closed sampling, this one is so if you use this formula carefully, the key part, so this is basically variance between the cluster means. So it has to do with the SSB. So this one. Okay. So if you look at this carefully, you can move this m term goes outside, and then divided by the degree of freedom is here, right? So 1 over m minus 1, 1 over m minus 1. So this becomes sb square, this one, sb square divided by m. So you have this formula. Note that on the simple random sampling, the sample size will be under the same sample sizes. The sample size is small ni times m. Population is n is ni times n. So if you use this sample size and from the population size, the sample mean will be 1 over n, which is ni times m, and then this is the sampling fraction, and then s square. So if you compare these two, the only difference is this, right? So the natural question is, which one is smaller? So basically, which one? So that is the question. Okay. The problem of comparing two sampling designs under the same sample size is an important practical problem, and the benchmarking design for comparison is a simple random sampling. The Leslie Kish introduced the concept of design effect for efficiency comparison with the simple random sampling, and the definition of design effect of a particular sampling design P is the variance of the sampling under the current sampling design divided by the variance under the simple random sampling under the same sample size. So if the sampling design has a design effect greater than 1, that means the variance is larger in the numerator, right? The variance of the current sampling design is larger. That means the current sampling design is less efficient than the simple random sampling. So another usage of the design effect is to determine the sample size. Since we know how to find the sample size for simple random sampling, we can use this information and the design effect to obtain the sample size for this particular sampling design. So the following step can be used. So step 1, so suppose we have a desired variance. Okay, so this could be like a length of confidence interval, like margin of error. So from the margin of error, something or desired accuracy, we know what the variance would be. So that's a target variance, and then from the target variance, we know how to compute the sample size on the simple random sampling. So if the sampling design is a simple random sampling, then we know how to find. Basically, that is essentially s square is a V star, right? So that is the so if s square is known, and this V star is given, then we can compute the sample size on the simple random sampling. Of course, we ignored this. So this one is ignored. And then given n star, basically we apply the design effect, multiply design effect to obtain the sample size. Okay, why this one is working? Because the variance of the y bar using np star, okay, using this np star is what? Is design effect of the variance simple random sampling y bar under the same sample size. Why? that is the definition of the design effect. The design effect is variance of the current sampling design divided by the variance of the simple random sampling under the same sample size. So the VP is design effect times variance simple random sampling, right? So that's exactly is here presented here, and then you can see that this one is basically times NP star S square, right? So given NP star means that excuse me, the NP star does using the sample size NP star. So now using this formula, right? Oops. Then what? Then what happened? Okay. Then this formula implies that this one is equal to 1 over n star. Okay. That is here in step 2. So then that means that is because of this, right? So that means we have a design. It satisfies the target variance. So basically, n star is the sample size on the simple sampling. So this n star is the often called effective sample size. So n star is what? NP divided by design effect. So this is the actual sample size under the current sample under P and design effect. So it is sample size required for the given n star if the sampling design is simple enough sampling. Okay.